Thank you for joining me to follow up the chapter 3.1 stress strain curve, and the course is solid state physics. So what we will do in this lecture is that I will introduce what is a stress strain curve, and I will very briefly go through its main regions and the related parameter values. Especially I will focus on yield stress and yield strain, because these are the values, properties, or threshold values that provide us an introduction to the follow-up subchapter, mainly when we go into the elastic deformations of solids. So this is, in a nutshell, what we will be covering in this quite brief lecture regarding the stress strain curve. And this is a nice topic, because it really provides us an outline for the rest of the chapter. So please memorize what is a stress strain curve after this lecture. It will be very useful for you later. And now what we will do is that we will want to understand how typical solids behave. And how do we do that is that we will introduce to you a stress strain curve of a solid, and how we come about with a stress strain curve is that we perform a tensile testing for the material. So we will stretch. We try to stretch the material, and we will, once we know the force, how much of force we are applying, and if we can measure how much the material is being stretched, then we can characterize the material by taking use of the stress strain curve. And this is how it looks like in practice, the stress strain curve. And roughly, there are different materials, of course, they have quite different stress strain curves, but conceptually, this is a good representation. So we have different regions, and maybe I should start by just pointing out the obvious, that on the x-axis, we now have the strain, and on the y-axis, we have the stress, the applied stress. And this is tensile stress. So we are stretching the material, and then we are measuring how much the material is being strained because of applied stress. So don't be fooled about the correlations here, what is being imposed on the material. We apply stress, and then we measure strain. But somehow, I don't know why, maybe for historical reasons, strain is x-axis is being used to describe the strain, and y-axis is being used to describe the stress. I do not know why it's this way around, but it is, and this is the notation we're also using. But after you've been dealing with stress strain curves for a short while, at least I don't find it bothering that the applied force is actually on the y-axis. But okay, now we have different regions. So we have a region that we call elastic deformation region. So with this vertical dashed line, I'm highlighting that in the beginning of the curve, we may have a region where the deformation of the solid is elastic. So when we apply a given amount of stress, the material is being strained, but when we reduce the stress to zero, the material returns to its original dimensions. And this is what happens. And this is why we're calling this regime elastic, so that the solid does not deform permanently. After elastic deformation regime, we will have a plastic deformation regime, and this is not always present in different materials. So if we have a brittle material, we don't tend to have a plastic deformation regime, but rather the material goes right away after the elastic regime into the fracture part and starts breaking down. So depending on the material that we have, we may have plastic deformation regime. And then this regime is being often divided into different other sub-regimes. So for example, there's this so-called easy glide regime, where already a tiny bit of increase in the stress will increase the strain of the material quite a bit. so that the slope dramatically changes when we go from the elastic deformation regime to the easy glide regime. And then after a while, we start having a so-called work hardening regime. And I won't be spoiling the fun, so I don't speak about much of this regime now. That will be covered later, and then we will have necking. But something starts happening here, mystical things starts happening. Not so mystical, we will learn later. And then ultimately, the material will break down. So this is what will happen in general. And this is a good approach because like it provides us a logical outline. So that we will start in the chapter by discussing elastic transformations and deformations and associated physics. Then we go to cover the plastic deformation regime, and then finally we go to fracture. So now you see the logic in our table of contents for this chapter. When we apply a small stress and when the subsequent strain is quite small, so usually of the order of percent, the solid is elastically deformed. So then we right away see that this first part is actually highly exaggerated, so that this is actually usually would be very steep. The curve, the slope of the curve here in the elastic deformation regime, and then it would usually be very narrow, but it's easier to draw these not in proportion, so we better understand and appreciate the differences of the regimes. And what's the kind of quantifying property of a solid when we are still in the elastic regime is that when we put the applied stress to 0, so it vanishes, the solid returns to its original shape. And this is what happens when we are still in the elastic regime. And subsequently, what happens is that we will actually have a linear relation between the applied stress and the induced strain. As we can see from the figure, it looks like a linear curve, and it is, in fact. And subsequently, we can deal with the math that is very, very similar to what we can we can derive from Hooke's spring law. And this is quite useful because it simplifies our mathematical treatment. And we can even predict how the material will respond if we would know the linear relation. And what happens where this regime ends is that we go into the plastic deformation regime when a given value of stress we call yield stress, and a sigma y we use as a symbol. So when we exceed this value, then we are beyond the elastic regime. And the respective amount of strain is known as yield strain, and the symbol that we use is epsilon y. So this is the kind of crossing point of these two dashed lines here, and this is the point that ends the elastic deformation regime. And after that, we are in the plastic deformation regime. And then when the stress vanishes, the material does not any longer return exactly to its original shape. That's what happens beyond. So, like I just said, at the plastic regime, part of the strain becomes permanent, and this is the defining property when the solid is on that regime. And depending on the different materials, this region varies quite widely. And for example, some materials don't even deform plastically, but fracture right away when the yield stress value sigma y is being exceeded. And when this happens, when a material has this property, we call the material the solid a brittle material. And examples of such a material are, for example, glass when it's in a solid form, so that it breaks down quite easily. Cast iron is another example of a brittle material. Others may have a plastic region, and when they do so, then these materials are being called ductile. And for example, most metals are ductile. This is the prime example I have. For example, aluminum foil is an example of a ductile piece of a solid, so that you can test around how ductile material behaves, and then you see it yourself. Everybody has aluminum foil in their homes, or if they don't, then shame on you, because come on, you're a physics student, or you're at least on a physics course. You should definitely have these kind of materials at hand. And then the final region that we will be covering is that we go into the regime that the stress is actually strong enough that the material will break down. And the scientific term or material scientific term is fracture. That is what every material will face eventually when strong enough forces are being applied. And what we will do in this chapter is that we will go into these different regimes and subsequently what happens for the materials in more detail. And we will be covering these different regions of deformation. This is what we will do. And we will start with the elastic deformations, because that's the first on the pipeline. And there we will be focusing on the macroscopic properties of deforming solids. And we will first do that. So we will define the properties and they introduce the terminology. And after that, we will turn our focus to the microscopic picture. So we want to understand how we can understand what happens on the macroscopic scale from the microscopic point of view. So I'm here now at the end of this first lecture, and this was about stress strain curve. So I thank you for following me, and next we will go and start discussing of the elastic deformation regime. Thanks and bye-bye.